Hello there. This is my Sony Sobox ICC-1600 from 1970, a calculator that I reviewed 7 years ago on this channel. It's actually one of my first videos ever. And I absolutely adore this thing. It is glorious. It's just so early in calculators, the magnetic reed switches, the Nixie displays, the construction inside. It is absolutely fantastic. It's still one of my favorite pieces in my collection, and it is the thing that I say that I will grab first to run out of the building with if it's ever on fire. But this thing did light another kind of fire in me to try and find some of its predecessors, and I finally have. So today we're going to be taking a look at this. This is a Sony Sobox ICC-400. This calculator is from 1967. That is a 58-year-old calculator. There were not a lot of electronics that came out before this at all, let alone calculators, and especially calculators that look this correct. Now, this isn't the only calculator we're going to look at, though, because I also have a Sony Sobox ICC-550, which came out sometime between the 1967 400 here and the 1970 ICC-1600 here. I don't know the exact date because Sony released a bunch of models like this, and this one has not been well documented. Technically, this calculator may have also come out in 1968, but it's really hard to tell. The true first model line in the Sobox calculator series was the 500, but I haven't got one of those. But honestly, between the 400 and the 550 here, I'm good. I think that I've got some pretty jamming examples here. Unfortunately, the 550 does not work, but it was sold to me as working and was shown on in the listings from when I bought it. So I'm hoping it was just cracked solder joints from the shipping. So today we're going to tear this thing apart and take a look at it. But oh boy, are we in for a treat on the repair process for this thing today, because it is going to be a very unique experience, because these are probably the oldest electronic devices that I will ever own. They don't even use chips. This one technically does, but it is very early custom Sony chips that are just integrations of transistor groups. These use little boards that are dipped in epoxy made out of individual transistors. They're not technically integrated circuits, but they are module circuits. So that makes these pure transistor logic calculators, which is just phenomenal. Such a cool concept that just had to be done at some point. But that's not even the end of the delightful wonders awaiting us in these, because these calculators don't have any RAM. Now, if you haven't seen my video on the ICC-1600, I would highly recommend you do that. Not just because it would get me more views on that video, but I don't really have a reason to open it today because it works fine. I was able to fully clean it out, sort out its issues, and here it is, still running great 7 years later. So we're going to have it here for a comparison with the other Soboxes later, but for now, we don't need to have it on, and I'm going to set it aside for now. Now, I am giddy with excitement over the sight of these two calculators here. Oh my gosh, I've been after these for years, and all of the stars aligned for these to be the ones for me to get, and I'm so excited about it. The 400 here appears to be fully functional, which is absolutely wonderful. We don't have to tear into it to try and fix anything. The 550, like I mentioned, doesn't work, and its symptoms are just no signs of life at all. The power supply is outputting voltage though, so I'm really hoping it is cracked solder joints from shipping, so we'll see how that goes. But these two machines are absolutely wonderful and are worth discussing a little bit further before we start to tear into this one. The Sony Sobox line of calculators were not something Sony really wanted to make. They have a company history that talks about the development of some of their devices, and I've referenced this for other videos in the past for things like the 3.5-inch floppy disk. But the development history for this machine is that one of their engineers kind of went rogue and just made it themselves out of scrap parts. Now, that engineer ended up winning them over, demonstrating how the calculators could be made out of subpar quality transistors that would have been trash elsewise because they weren't quite good enough for other applications. So with that, the project was greenlit and it went on for further development. Now, the first version of this calculator shown to the public was the MD5 prototype at the 1964 New York World Expo. Now, this calculator was extremely notable there for being one of the first fully transistorized all solid-state electronic calculators. Now, I say one of because Sharp also had a calculator there, but the Sharp used a key grid like this comptometer, not the keypad that you see on the Sony Sobox. The Sharp overall seems like a look back at calculators, making old designs new, whereas the Sonys are looking forward into the future of what could be. You have to keep in mind here, this is an all-new device. Now, the Sharp released first, which means that this calculator doesn't get to claim any historically notable firsts, but it is still a very solid machine in how it works. Speaking of solid, I have an interesting anecdote about something. Sobox. This is the name for the product line that is these calculators that Sony used. Now, that stands for Solid State Abacus. Now, Solid State Abacus doesn't really gel with Sobox, at least in English. I think the word abacus in Japanese ends up being a little bit closer to Sobox, and it's kind of a portmanteau of sorts there. But I think they also came up with a way of making it make sense in English that I haven't seen many people cover. This ad for the ICC-400 calls this the Sony answer box, and that, in English at least, sounds a lot closer to Sobox. Sony answer box? Sobox. I found that while I was researching these devices and just find that to be a fun little detail that I haven't seen anyone else cover. Now, that's about enough history on these machines, but there is one more thing I want to point out before we take this one over to my workbench and start to tear it apart to try and diagnose it. And that has to do with the 4 holes and this connector on the back. Now, these are desktop calculators, but they're also portable calculators. A battery pack option was sold that would mount right here on the back and plug into this DC power connector. That is why these calculators have a handle. I don't really want to carry them by the handle because the plastic is 58 years old, and I don't really want to put the full weight of this machine onto the little screws holding this into the very brittle old plastic. Now, but I do find that to be a funny thing because these are not small calculators, and having a battery pack on them would only make them heavier and less practical to carry around. All right, that's enough of the history for now. Let's get into the mystery of what is inside of this machine and why this one doesn't work. First off, though, I haven't actually plugged this into power the whole time I've been showing you this for now. So I do have it plugged in here, and it's on a kilowatt, so we can see how much power it draws when I do this. So we can see it is drawing 6 watts, but we are not getting displays here. So it is drawing power, but not fully functioning. Now, for comparison, let me go grab the other one and plug it in. I'm just going to run it off to the side here. So we're drawing the same amount of passive power, turn it on, and we are getting about double or triple the power draw. So 10 to 15 watts. So something somewhere is not getting power in this thing for sure. So let's start to open it. Now, to start here, I'm going to flip it upside down so we get to the screws. I'm going to put some foam on top of it like that, though, although under it, so I don't have to put it on the handle. And I'm going to flip it around because here we can see the same weird kind of screw that the ICC-600 used. My most optimal tool for this is still this pair of needle nose pliers. So I'm going to go in there and loosen that. But also, like the 1600, this is a retained screw. All right, with that screw loosened, now we can remove the bottom, which doesn't get us access to a whole lot. The disassembly continues with these spring latches that you have to move into position to be able to remove the top from this component. So I'm going to pull both of these back, and then the top releases. This is frankly a fantastically put together device. Now, we still don't have access to anything here. The only thing we can now even begin to see is the power supply located behind this mesh. But we can continue the disassembly, and it continues to be toolless from here because we need to pinch these little metal tabs in, and then we can pull out these, I don't even know what to call this, these pins. This is just wild how this thing goes together. One on each side. Now, this thing still doesn't come apart here. The next step is to pull these tabs out, which pushes that in because this is the latch that holds the power supply in. But before I do that, I'm going to feed some of this ribbon cable up because that's going to give me some slack as I move the power supply. Push that and pull slightly. Push that, pull slightly. And now the power supply is... Oh, come on. Loose. There we go. And now we can finally get access to what makes this thing insane. This is a backplane device, just like the other calculator. We can see each card has a designation letter here, and they are in a slant order, so it's going to be pretty easy to keep track of where these cards go. But we can also see the dipped hybrid modules that make up the transistor logic of this thing. All of those things hanging down are groups of transistors and other components that make this thing work. It's just insane. Now, I mentioned this is one of the best and worst solder devices I've ever seen. Let me take out one of the best soldered cards I've ever seen. These have the legs folded over, but they're folded over flat and soldered on extremely well. I've never seen this assembly method before, but there's no angular ring. Instead, the trace just goes over to the hole, the leg is bent flat, and then soldered directly to the trace. Every single leg I see on here soldered in this manner looks absolutely fantastic. This seems like a pretty solid way to do this. And again, I'm just surprised I've never seen this before. Now, though, we're going to contrast that with some of the worst soldering I've ever seen, which was done in the standard method with annular rings, but on a single-sided board. I'm going to take this out, though, because I have a feeling this is where my problems are. Before I flip this thing over, though, oh my gosh, just look at it. It is absolutely insane. These boards are incredible. I love the aluminum trim around the outside. It's just, oh, it's so cool. But this is the side that is absolutely horrifying. So here it is, and just, ugh. So first off, we have legs that are just, is that one even connected to solder right there? That doesn't look great. We have legs that were just cut with giant pliers right there. That's awesome. Another one that just absolutely looks detached there. We have the weirdest vias I've ever seen. That is a through hole. Nothing actually is connected there. Another disconnected section. Just what on earth is going on there? Yeah, so this one is pretty awful, I would say. This has about every bad solder tactic that you could have from this era. Like that one right there, that looks possibly bad. And the whole thing basically looks like this. Every single place you look, what is going on here? So here's what I'm thinking. This board probably should just be entirely reflowed. So I think I'm gonna work on that for a bit here, and then we'll put it back in and see if it fixes anything, because just, my gosh, this is awful. I'm gonna do some post commentary here because this repair process did not go at all how I thought it would. As I started to reflow the solder, I was getting these burnt, charred clumps showing up. And this told me that there was more to this. And when I got the light on the board at just the right angle, I was able to see that it was conformally coated. Now, this is a moisture barrier for protecting the board from corrosion, but this is a kind of weird use case for that. I don't know why this calculator needed it, but it did mean that it was impossible to reflow all the solder, though, because anytime I would try to melt the solder, I would burn the conformal coating off and probably contaminate the solder with it. So I needed to remove that before proceeding. I tried scrubbing it off with some 91% isopropanol, and that did nothing. This stuff is way tougher than that. I had been posting about this process on Mastodon, and TubeTime there had recommended that I use acetone. Now, I am not a huge fan of acetone because it is some really aggressive stuff, but this was also some really tough stuff, so it seemed like that was what I was going to have to use. I went and I picked up some acetone locally and tried that on a small paper towel while wearing gloves to see if it would work, and it did work for dissolving the conformal coating, as well as dissolving my gloves. This is why acetone is some really nasty stuff. But it was going to be able to solve the problem, which meant I needed to form a plan for how I was going to work on this. My office is not well ventilated and I can't open any windows, so I wasn't going to be able to do this there with the fumes from the acetone being probably lethal in the concentrations that I would need to use it here. So I decided to take the whole calculator home so that I could work on it in an open air environment. After dismantling it yet again at home, I brought the board out into my garage where I could open up the doors and run a fan to blow air through. I then proceeded to spend a half an hour scrubbing on that board trying to get all of the conformal coating off. I had to completely drench it to get it to come off. The acetone was making it sticky and it was clumping up as it was coming off. It was really tough and not a trivial process. Now, to even be able to do this, I had to buy some butyl rubber gloves to be able to withstand the acetone for long enough to actually clean it. These were expensive, but definitely necessary for this process. But after that half an hour of cleaning, I could tell by moving it around and getting light at different angles, it was finally clean. I got all of the conformal coating off. So it was time to bring it back in and try reflowing the board. And even that didn't go like I expected. It turns out there was already some kind of contaminant in the solder, and the horrible looking solder joints were actually from the solder bubbling as it was being heated. I have never seen this before. It is super weird, and I wasn't sure how to approach this. I didn't have my desoldering iron at home, and I really didn't want to desolder every single pad on this thing anyway. That's a lot of stress to put the PCB through. I never really solved this problem. I was adding fresh solder, but that wasn't helping enough, and what I ended up doing was pulling the iron away slowly. That way the rate that the solder cooled was slower, which helped it stick more, I hope. I don't know. This is such a weird problem. I'm really not sure if what I did was the right call. But I did go through and reflow the entire PCB like that. I stopped filming once I realized it was going to take as long as it was with this weird problem. But after I got it done, I put it all back together, and that wasn't the issue. So what next? Well, the common thing to look at is the power supply. Now, I'd mentioned earlier that I had checked the voltages coming out of the power supply and they seemed fine, but I don't actually know what every single connection coming out of the power supply does. There are no schematics or manuals for this stuff, so I was just guessing because some voltages looked good. So I decided to open it up again and see if there was anything suspicious in there. There are a lot of large components in there that could have rattled loose on their solder during shipping, so it seemed likely that there could be something wrong there too. After I got it open, something hit me that I just can't believe I missed before. Right there on the board was this red-coated inductor that one of the legs had corroded off of and come loose. Now, one of the parts in the power supply missing a leg? Yeah, that is definitely the kind of thing that will take down the whole device. With that in mind, I brought the calculator back to the office so that I could work on it there because the scope of the problem just changed. I was also able to tear apart the ICC-400 to compare the two. Both of them have what seems to be the exact same power supply. And this gave me the option that I didn't initially want to do, but I ended up doing anyway. I pulled the same inductor off of the ICC-400 so that I could measure it in case I needed to buy a new one for the 550 because, well, the leg was corroded off. This is also actually the first time I've measured an inductor with my LCR meter. While I had the inductor out though, I kind of thought, I should just put it in the 550 and see if it works. What if it wasn't that and I was wasting my time even more? So I soldered the 400's inductor to the 550's power supply, and that worked. Oh man, that was such a relief because I hadn't seen this calculator fire up at all yet. Now, with the knowledge of this calculator would work, if not for one leg on one inductor, I started to form a plan. Since the inductor seemed to have been ceramic coated, it probably didn't corrode all the way up the leg. So I started scraping back some of the coating, and I did find fresh copper for that leg. So I soldered a leg from a capacitor that I'd replaced in something else on there, and decided I was going to try and reuse the original inductor. Now, this still wasn't going to be a super easy repair, but let's see how that worked out. All right, here's what I'm doing. I've got, I think, both through holes clear here, but the solder's on the sides. got the legs on there. I made one that I had to repair extremely long, and I have an idea. So I'm going to feed that through there. All right. And then the actual connected leg is right there. Put that down there. Okay. So that is one side connected. Now the other side, I'm going to bend this over a lot. I'm going to apply lateral pressure so it puts the force on that. And then that might work. And that to there, and I'm going to tack it over there. Okay, I think that'll do it. That might be repaired in the weirdest way possible. All right, moment of truth with the original inductor. Yes! That will probably be both of these fully functioning. Oh, that's so awesome. All right, with this thing working now, I'm going to do a little bit of cleanup and other minor things. So here I'm just gluing on a spacer on the ICC-400's power supply board. These keep the PCB from hitting the metal contacts on here. I'm potentially shorting, just adding extra space. They're probably not necessary, but while that is curing, I'm going to go ahead and clean these up a little bit because I'm not going to be able to get to the Nixie tubes once the front cover's back on. I'll also wipe off the inside of that. But before I put this one all back together, I'm going to take out all the board so I can walk you through what all is in here. You have had a peek of that while I was removing the conformal coating on the top board, but you haven't yet seen the best part of these. As an aside here, these tubes have way lower use than my ICC-1600, so that's kind of awesome to see. They are nowhere near as darkened from sputtering. And this is true for both. It's looking so much better than it did when I first got it. And we're all ready to take a look at what makes a Sobox tick. All right, so let's take a look at what we've got in here. Now, I have literally no idea what any of these boards do. There are no schematics, there's no service manuals or anything like that online. So all I know is that these are boards and they have the Sony hybrid chip modules on here. So these are, I think, ceramic boards that have transistors put onto them and then they're epoxy dipped like that. So each one of those is basically another PCB that is just soldered directly to this PCB. So depending on how you look at it, this is either a small scale integration device or a discrete transistor device. I think both kind of apply personally. Next up is one of the boards that has the much less insane soldering method, and it is almost nothing but those parts. Now, again, I don't know what these boards do, but we can take a look at them all here. Those two are not quite the same. That's wild. Then we get to the last normal board here. That one's got, yep, more stuff on it. But then we get to the insane part. It's one of the things that makes this just one of my most favorite devices I now own. This is the memory, but like I said, it's not RAM. This is a delay line memory module. Now, before we get too much farther into this, I'm going to let you know I'm not going to open this. This is an electromechanical device, and I don't want to potentially mess this thing up inside. This calculator works. If it didn't work, if I wasn't able to repair it, I was considering opening this up. But since it works, I don't want to risk it. Because inside of here, we can kind of know what there is, thankfully, because there's a Wikipedia image of, I think, one of these modules. But we can see a coil that is wrapped around the center. It goes to a transmitter on one end and a receiver on the other end. The transmitter end twists the cable and sends a torsional shockwave that travels along the wire. It is then picked up by the receiver on the other end. The time between the transmission and reception is the memory. It is a time-based memory device using the mechanical wire's movement. Now, this is wild. And there were several devices, especially calculators, that use this kind of memory. They were typically a lot bigger than this, though. So this is one of the smaller ones. I think this is absolutely fantastic. I am over the moon to have a delay line memory calculator finally, and just this is so cool. So this is why the calculator does not have RAM, because it has to wait for all of the memory to come through the wire every single time and then act upon it. It is cycle dependent, which it's just it's so crazy. Now beyond that, we can see the back plane inside of there, and unlike the Sobox ICC-1600, we can see that there's actually some stuff going on in there. So I suspect that the cards all must go back in a particular location. And this is as far as we're going to go. While I would like to show you the Nixie controller and the keypad, this is a far more difficult to disassemble device than the 1600 was, and I have a feeling it's going to be very similar to that. So I'm going to again refer you to the ICC-1600 video, where you can see that this has magnetic reed switch keys. These ones are also slightly different, and I don't think they come apart as cleanly, just directly exposing the raw reed switches. So if you want to see how the keys in this work, I highly recommend that video. For now, I'm going to put this thing back together and relish in the fact that it hopefully still works after taking it apart here. Before I finish putting this back together, the top on the 550 is pretty gross, so I'm going to go ahead and clean that up a bit. There we go. Way better looking. The 400 was just better as I got it. All right. They're all cleaned and put back together. And that is 3 functional Sony Sobox calculators there. Oh my gosh, that is such an exciting sight. Now, we're going to run through the different features that these have and how they work, starting with the least equipped, going to, well, it's debatable which of these is the most equipped, but we'll get to that in a moment. So we're going to start with the ICC-400 over here and run through what it can do. All right, so here on the 400, let's go over everything just to get a familiarity with the machine. So starting from the back towards the front here, we have the Nixie display, which I think is 12 digits. Let's just count this up real quick. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 digits. That's a lot of digits there. You might be able to tell the variable depth to the digits in the Nixie tubes there. That's just a function of how they work, and it's quite a unique experience. They're so cool. Now that lever that I moved here is the decimal point slider. You can move this to any one of the digits on the calculator to change where your floating point is. So that's a pretty handy feature there. From there, we can clear everything with that key, and we can begin. So we start out at a 0 input in the register that we can see here. Now I'm going to call this the visual register. There would be several other registers in here, but it's kind of strange being, you know, the delay line memory. I'm not exactly sure how all of that works, but we can cover a few things that are very register-like here. Now, first off, this is an algebraic notation calculator. So if we do 1 plus 1, we are left with the value left in the display, and we hit equals to show 2. And this is your classic 4-function calculator. So from here, we could do -1 to get a result of 1. We could then multiply this value by 5, and then we could divide a value here. Let's divide this by 6 and get a decimal value there. Now this also supports negative numbers. We can see a negative indicator sign over there. So if I wanted to do, say, -5 here, we can do that, and we can get a minus indicator saying this is -4.167. Now, interestingly, this is slightly different from the 1600 here. If I clear this key, which, by the way, this is a clear everything key. This is the clear entry key. It's not very well marked. I can demonstrate this. So we have the visible register here, which is now 1. If I do a plus and then input 2, if I hit clear here, we've only cleared the input register. If I do 2 again and then hit equals, we can see that we have 3 there. So that's why we have 2 clear keys here. Although we actually have 3 because this has an additional function to store a value. I'm going to press the memory in key here. We can clear everything except that this does not clear the memory stored value. We have to hit MC for that, which will then clear that. And actually it just resets it back to 0. Now, speaking of 0, this calculator has a function that it's easy to overlook for how good it is. So I'm typing a number here, 1, 2, 3. We'll hit equals to set that as our register value. And the thing is that there are no prefix zeros on here. Now, this is one of the first electronic calculators like this, and they just knocked that out of the park. They knew not to light up the digits in front of that. That's a feature that they would have to build into this thing. And they just got it right on the first one. It's such a cool thing. Now, there are 2 more features on here that I want to take a look at that are shared between all of the calculators, though the 1600 has one more thing going on with this, and that is the rounding switch. So if we do, say, 5 divided by 6 here, we can see that we have 8.33, and then it cuts it off. If we remove this rounding here, we can do 5 divided by 6, and we'll see it's 8.33333. We can see the same thing here with 1 divided by 3 versus 1 divided by 3. That allows it to more quickly get through the calculation because it's not a very fast calculator. As you can see, when you do a division, let's say 8 divided by 7, it has to think about that for a moment. Let me get some slow motion footage of that. Now, the final feature that this has is the R key. And what does that do? Well, let's look at this thing really quick here. On the top of the calculator is this handy guide that is located underneath the handle that tells you how to use the calculator for common functions. And it has on here descriptions of what all the keys do, including the R key, which is the R key. It's not tremendously helpful, Sony. You actually labeled all of the other keys, but then the R key is just R key. Well, I know what the key does. So we're in luck here because I can demonstrate this. So the R key is a ratio key. That's what that means. So we're going to do a percentage calculation using the R key, which is such a cool feature to be able to do on this. So let's make this really simple to start with here. So I'm going to input 10. We're going to put 10 divide and then 7.5. So we now have a 10 and a 7.5 in here. And this is weird because it's going to kind of flip these for the ratio so that we just keep that in mind. I'm not using like the divisor or the operand here because the order here is a little weird, but we can push ratio here and then equals. There we go. We have 75% as our result. Actually, I was wrong there. I was reading through that card that goes on top to see what the R key may do and some of the limited examples it has, and it made it seem like it might be related to ratios and percentages, but that's not even close. It's much, much more basic than that. And of course, if I just do 7.5 divided by 10, I'm going to get the answer of 75% there. No, what the R key does is so much more simple. So if I do 1 plus, we have now copied the 1 from the visible register to the hold register in the back, then type 2. We now have 1 in the hold register and 2 in the display register. The R key just swaps the registers. That's it. Very, very simple. Yeah, it's just a register swap key. But I didn't know that when I was initially recording. But that is the end of the features that this has on face value. You can do other things like raising to a power, which it says you can do on the directions there, but those are just combinations of multiple functions. So for truly new functions, it's time to move on. So here we have the Sobox 550. Now I'll mention that the difference between the 500 and the 550 is basically this key and this key, if I remember correctly. The 50 added a little bit more memory to the delay line module, which allowed them to add these features. And those two features are basically what differentiates this model from the 400. Let's start with the total option here. Now, what the total key does is add all of the answers to the equations that you give this to a running register in the background by accumulating them. So we have just added 3 to that register. If we do 6 minus 2 here, our result will be 4. We've now added 4 to the register. We can read this register at any time with the subtotal key, and we can see our value of 7 there. The subtotal key did not exist on the 500, and you would have to do something different for that. Let's make this end up with 10. So we're going to do 4 minus 1 equals. So we now have our value of 10 in the total register. And when we release this, we will get 10 printed to the display. So on the 500, in order to see your total value, you had to destroy it, because once we depress this key again, it will clear that value. So the total feature is a really handy one if you're doing a lot of monetary equations where you need to come up with a running total cost or something like that. Definitely the kind of thing you would see in a calculator. But this one is a little weird. This is the constant key, and this stores a value and I think an operation in the calculator to execute repeatedly. Now we're going to do 5 times 2 here, and we're going to hit equals. We just got 10. But now we can hit 3 equals and we get 6, and 8 equals and we get 16. We have stored the multiply by 2 function to this, and now all we have to do to multiply anything by 2 is hit the value and then equals. That is a cool feature. Now let's try this a little differently. We're going to stare the constant. Let's do 10. The first number doesn't really matter here, but minus 2 should. So now if we do 6 equals, we get 4. 9 equals, we get 7. I don't know why you would do this with other values like that, unless maybe you were trying to, calculate a fee to be added to any number. Maybe your fee value is really complicated, but that's a pretty cool feature there, I think. Now, everything else here is basically the same. We still have the ratio key. So if we do 20 divided by 4 and we do ratio equals, we can see that that is 20% of 20 there. So cool. We have the memory storage and all of that. It's functionally identical elsewise to the 400, except for the total and constant values. Now let's finish this up by looking at my 1600 again. Now the 1600 here is a kind of weird thing. We have the total key, but we lack the subtotal key. We have a way of setting where our decimal point is, but it's not the handy slider, and it's not as functional as the others. That's probably good enough, because realistically, we don't need to be able to set it to every single digit, but it is a limitation. And this one is weird because it has the change sign key. So if we have 1 plus 2 here, we store that, we press change sign, and my key has gone back to sticking. I'm guessing the plastic is expanding, but we can see that that changed the sign. Now, I've actually not tried this. If we do -5 plus 2, okay, we do get -3. I don't know why the change sign key exists. It's like it's just a multiply by -1 as a permanent key in there. I don't understand why it's there, but that is a feature that the other calculators don't have. Now, the only other feature that this calculator has is an additional rounding point, but it's really not that different. We can go up to the same rounding point as the other calculators. I'm going to give us slightly more digits here. We're going to do 1 divided by 3, and we can see that we have 2 spare digits there on the end. And then we can go down here to the other value, 1 divided by 3, and we can see we just have 1 spare value. I guess that's, a feature, but it's not that distinct. Now, while I have these all here, let me answer some of the other kinds of questions that I typically get when I showcase weird old devices that have inputs. The keys, what do they feel like? Well, they're literally springs that bottom out. So there is no real feel to these. It's just a straight linear force until it bottoms out, which is fine. I mean, they're just calculators. The force of the spring is realistically the only variable thing between these. Now, this one is a little weird, the way that this key grid works. This one is inferior to these, I would say. These are individual magnetic reed switches. This is a block that holds all of these in. That's why my change sign key here gets a little stuck, because the key stem is expanding because it is cracked and is fitting into the block a little bit more tightly than it should. Thankfully, all the other keys still work fine, and that's arguably the most useless one. Now, these also have the absolutely fantastic Nixie tubes. These all look really, really good. Like I mentioned, these two are extremely vibrant. These are slightly bigger Nixies than this one, for sure. This is smaller. I really didn't realize how small those were. These, I think, are the more common size for Nixie tubes, although they're definitely not the big ones, but they're really, really nice. I guess one downside to having the Nixies be so large, the tube is round and the Nixies are spread out more into it, so there's a lot more variance in depth on these Nixies than this one. I would say that the filaments are also thicker on these Nixies than this one, so it's actually a little bit more difficult to read the numbers that are behind all of the other filaments, but it's still an absolutely fantastic device. Well, all right, I think that about wraps it up for the Sony Sobox calculators here. Oh my gosh, I am still over the moon that I managed to get my hands on these. The 400 is just such an early, wonderful little calculator. The 550 is a minor evolution on the 500, which just makes it that much more usable. And then, of course, I still love the 1600 here. Now, I said at the start of the video that the 1600 would be the calculator that I would grab first if the, building caught on fire or something. That would be the one thing that I would grab to make sure it was saved. Well, now I don't have enough arms for, all of these. So I guess I'll just have to take this one home. And then I only have to worry about 2 of them. But I think that's going to be it for now. If you enjoyed this video, you may want to subscribe to the channel, because it will definitely not be the last weird old calculator video. I still need to find one that's got a CRT and maybe one with some core memory in it, but I don't know when I'll find those. If you want to help support the channel, I am on Patreon, but for now, that's it, and I will see you next time.